Okay, now, one of the first things we looked at in lab last week was what happens if you have a magnet and move it around in the vicinity or do various things with a magnet and a coil of wires where we have this circuit connected to a galvanometer. Okay, so the galvanometer deflects one way or another when you do that sort of thing. Okay, and it turns out that what we're really looking at is changes in the flux that you get from the magnetic field here. So you got a magnetic field. Let's just pretend the magnetic field's all in this direction. So if I move this thing closer and closer to the coils and then through it and beyond it, the magnetic flux increases because we're closer to the magnet, basically. There's more to it, and you take into account the shape of the magnetic field. We'll talk about that later. But basically, we investigated that, and then I explained or asserted, didn't derive it. We've got to derive some stuff in monovariable calculus if you want to do this rigorously. But we have a magnetic field B, function of position in space, could be X, Y, Z. In that situation, we might want to use cylindrical coordinates with the Z axis parallel to the central axis of the coils, and you like R theta Z and so forth. But anyhow, you got a magnetic field, and the flux of that magnetic field is the integral of B with area increment, meaning that we haven't talked about integrals, but it's basically if you had a constant B and a flat surface, well, that flat surface would have a normal vector, okay, wherever direction it's in, has a normal vector, okay? If you've got a magnetic field in this direction, if the magnetic field is uniform over some region that has this orientation, then you just take the dot product of the magnetic field with the area. Now, if the magnetic field varies with different parts of the region, you got to do an integral, and there's your definition. We'll learn how to do those integrals in monovariable calculus, but right now you don't really even have to understand that for the physics course. You're just adding up all the B dot A contributions of a bunch of little regions on the surface. Now, that's no matter what the shape of the surface is. We're going to talk more about flux today because what we're talking about starting this week is Gauss's law. Okay, and that's all about electrostatic flux, flux of an electric field. Now, the reason we're doing this in lab is we're anticipating the concepts and the fundamental ideas that we spend the rest of the semester on, pretty much. Okay, so we have this. Now, you have the magnetic flux. That's like the amount of magnetic field that penetrates a surface. Okay, if your magnetic field varies with time, and of course we have these relationships, you know, B dot dA is B cosine theta times dA. Cosine theta is the angle between B and your normal vector. There's your normal vector, there's B. Right there's the angle between B and your normal vector. So we're just adding this up. Okay, well, anyhow, the EMF or voltage we get in a circuit, then, at least in this circuit, is the rate of change of the magnetic field with time. Very simple. Okay, so that's what we mean by EMF or voltage, and that's our first introduction to voltage. Now we use some 1.5 volt batteries, so there's a voltage there. It's equivalent to the EMF you could get by cranking a generator that rectifies the circuit. Okay, and you don't need to know necessarily what that means at this point. But we have those generators, so you can produce like a 1.5 volt direct current And from a battery, 1.5 volt battery, which is one of the standard voltages, or you can approximate it by a rectified sine wave that's produced when you rotate a magnet inside of some coils in a hand crank generator with gears and everything. And we looked at that. So you kind of know what I mean. Okay, so anyhow, there's your EMF. Okay, so that's a voltage. Now, anticipating what's coming up in the very next chapter, once we have a voltage, we can define voltage a little bit differently as the work per unit of moving charge between 2 points in an electric field. So for example, if we got a charge Q here and a variable or test charge capital Q here at distance A, and then we want to move it to distance B, well, this charge exerts a force on this charge such that the work done on this charge from A to B is this quantity. Okay, the integral of K times the product of your charges over R squared with respect to R. The force is always in this direction, assuming Q is a positive charge. When you do the integral, you get negative K, big Q, little q over R from A to B. And that's really the most important integral you've seen so far in the course. Okay, so you really want to be familiar with that. You want to understand this completely, like right away, okay, because it's really easy. Anyhow, you do the integral, you get this, and we conclude that the work then per unit of moving charge is the work we get when we do this integral divided by the moving charge, which is our capital Q, which is this, and this is our voltage between A and B, okay, or the potential difference. We call it a potential difference. We call it an EMF. It's measured in volts. So, you know, we do traditionally call it voltage. So we answer the question, how much work to move the test charge from A to B? The potential difference is the work per unit charge between those points. We'll be more specific on it with signs and everything when we talk about it in a week. And voltage then is work per unit charge. Okay, and the SI units would therefore be joules over coulombs because work is measured in SI units of joules and charge in SI units of coulombs. Although coulomb isn't, well, we've redefined what we regard as the fundamental units. Turns out the amp is a fundamental unit now, and the coulomb isn't, but that's okay. Still has the same meaning. It's measured differently. Okay. Then we created a circuit. Okay. At a voltage of 1.5 volts from here to here. This is your 1.5 volt battery. The potential increases by 1.5 volts from here to here. So the potential increase from here to here is 1.5 volts. Now this whole thing here is like a wire, a thick wire, and I've indicated it as a thick wire. Connected to another thick wire. Okay, but this thick wire has what we call a high resistance. Takes a lot of voltage to get an electric current from here to here. This wire takes essentially no voltage. It's a wire of low resistance. This is a wire of high resistance. Lots of resistance and lots of voltage required to get a little bit of current through this thing. And we observed that, we observed, that we're getting a lot less current when we inserted this wire in a circuit that just consisted of these kinds of wires. Okay, now this is a closed loop, so that from this point all the way around back to this point, to move a charge from here to here takes zero work. Whether the charge just stays here and doesn't move, it's obviously going to be zero work, or whether it goes around the whole circuit, it's just conservation of energy, still takes zero work. This means that the net potential difference from here around to here is zero. So you got 0 volts from this point all the way around to this point, and I'm not sure I've got that. Yeah, okay, well, yeah, here's the loop. Let me color code it a little bit to make more sense out of it. To move from here to here is a closed loop requiring 0 volts. And this point really represents this point here. Okay. Now, to move from this point to this point, what's it take? Well, if it takes 1.5 volts, or if your potential, electrostatic potential, electric potential increases by 1.5 volts here, and it increases by 0 volts if you go from here all the way around to here, that means it must drop by 1.5 volts as you go from here to here. And when we analyze circuits, as we will later, we talk about voltage drops. The voltage drop from positive to negative. Okay, so anyhow, we saw that. Another thing that we then saw is, let's say that this resistance wire here, let me just kind of use a different color. This chalk is getting worse every time I use it. Actually, that's the wrong stuff anyway. Okay. That's our resistance wire, the one where the voltage really drops. And we could measure it. There's essentially 0 voltage drop from here to here, because this wire is a good conductor. It takes very little voltage to create current in this wire. And same here. So almost all that 1.5 volt drop is from here to here. I'll also qualify this, but indicating that there's probably a significant small resistance in the battery as well. There certainly is. We can measure it. Okay, so you have a little bit of voltage drop across the battery that I'm ignoring right now. And I'm just saying that, okay, your 1.5 volt drop goes from here to here. We'll refine this when we get into the details of the circuit. I'm just trying to get a general idea. So what we have is a 1.5 volt drop from here to here. It's a uniform wire, so the voltage drops at a constant rate with respect to distance from here to here. The voltage drop across this wire is about 50 centimeters long, this resistance wire, this nichrome wire. We have a 1.5 volt drop on 50 centimeters, comes out to 3 volts per meter. Okay. Or it's like 0.03 volts per centimeter, 3 volts per meter. That's our electric field. Electric field is, first of all, newtons per coulomb. Okay, the force per unit charge. It's also the number of volts per meter. And the connection is very simple. It's implicit in everything I've said already, but we'll make it more explicit. But just remember, there are 2 ways to write out the units of an electric field. But this has to be the units of electric field. Because we divide volts by meters, we divide joules per coulomb by meters, which means we divide newtons per coulomb, newton meters per coulomb by meters, leaving us newtons per coulomb, which is the other form of the units for the electric field. Okay. Now then what we did was we essentially set up a circuit. Okay, this circuit is right here. Then we tapped off a little bit of voltage by just attaching a couple of leads to close to nearby points on the nichrome wire. And we drove another circuit here. Okay, and we just put one of these generators in the circuit. There's a resistance within the generator. It's a little more complicated as the crank happens to be turning because that generates current, okay, itself, but the crank wasn't turning, so that's okay. And we had an ammeter here. We had an ammeter here. Okay. And one set of data we got was by varying this distance here, we got different currents here and some difference in current maybe here. Okay. So there was the data. It was basically the currents in the 2 meters versus the separation of the leads we used to tap current from the nichrome wire. I also quoted that Ohm's law, the voltage equals current times resistance. That's kind of relevant. Okay. We also observed by putting a compass over or under a wire that was carrying a current, that the compass was deflected when the wire carried the current. And compass normally pointed north, but that's the north is there, but it deflected right or left. And in such a way that it's at least plausible that if this is an end view of the wire carrying the current, that if the current's gone in a certain direction, it turns out if the current is traveling in this direction, which of course means electrons are traveling in this direction, we'll talk about that. Put your thumb in the direction of current, your fingers go in the direction of the magnetic field, which therefore surrounds the wire in a circularly symmetric way. And the current over the magnetic field over the top of the wire is like here. Under the wire, it's like here. Now that's consistent with what we observed from the wire and the compass. By rotational symmetry, which we kind of assume, we conclude that the current will go this way here, and this whole thing, the right-hand rule seems to work. We'll go more in depth there, but what we saw in lab is just a whole lot of the essence of electricity and magnetism that we'll be pulling together for the next 2 months. Okay. So what did we get that on video? Now we'll go on and talk about Gauss's law. Okay, go ahead and work on that. I'll just say it all again. We're doing Gauss's law. We're going to start just with the idea of a charge at the center of a sphere of radius A. And I guess I could, okay, radius is A, so. Radius is A. So I just want to know what the magnitude and direction of the electric field at the surface of the sphere is. So what can you tell me about the magnitude and direction of that electric field? Okay, so we've got a quick answer there. If I have, first I just got a quick direct answer, KQ over I squared for the magnitude. Okay, here's charge, S charge Q. Then we have our R vector here. And we have our force. Equals A big Q little q over A squared. What's the direction of the force? What can you tell me about the direction of the force? Okay, well, we essentially got this part of it, but we have a unit vector. We have to multiply by this. It gives us the force, and we need the force, not just the magnitude of the force. Although it's going to turn out in this case, it's only the magnitude that comes through. Barely got that in, but right there is Coulomb's law. Okay, so you start with Coulomb's law whenever you can. And electric fields, therefore, I'll get my norm signs in the right place. Okay. This could actually be that K U over A squared times R hat, where R hat is a unit vector in the direction of R. Okay. So electric field's a vector. It's got a direction. The direction is really critical because we now want to talk about the flux. And we want to talk about the flux through some small region on the surface. And I'm just thinking notation here. So there's some small region on the surface. It doesn't look like it's on the surface because it looks like it's kind of going outside of the surface. Might have been better to draw it here and draw some axes and get a perspective and everything, but this is a small near the position defined by the vector R. So we could assume we wish that this is the origin, so that the position is just designated by the vector R. Okay, it's the location of the tip of the vector R. So now what we've got is, so we've got some small region. We're going to call that region delta S. So here we have our region delta S. area is going to be delta A. In the direction is normal to the surface. So now we've got a delta S. And you've got a normal vector. We'll make it a unit normal. M. So to say, we just said some hand waving and stuff. Let's say that this thing is an increment on the surface of a large sphere. And let's say the center of that sphere is down there a couple miles away. Okay, so here we're on the surface. And you can see where the center has to be. It's got to be back in that direction, perpendicular to this surface. That should be intuitively obvious. But also, you could do a great circle, a circle whose center is the origin where the charge Q is located. Okay. And which then passes through this point. There are infinitely many great circles. There's circles in this direction and circles in this direction and so forth. Okay. Any one of those circles is perpendicular at this point or at this surface to the radial line. So this surface is perpendicular to the radial line, or very nearly so, since this is flat. But if the surface is 2 miles in diameter, or about 4 miles in diameter, that is 2 miles away, then at every point here, the electric field is very, very nearly perpendicular. It's radial, very, very nearly then perpendicular to the surface. So where's the normal to the surface? Well, the normal to the surface is also perpendicular, so it's either there or there. And since we talk about an outward normal from the sphere, it's going to be this way. Okay. This tells us then that in this picture, this unit normal is parallel to the electric field, doesn't it? Electric field is perpendicular to your R vector, which is radial, and the normal vector is radial. Okay, so they're parallel, maybe in opposite directions. The radial vector is in this direction. I've got the electric field and the force indicated in this direction, assuming both these charges are positive. But it could be that the electric field is back in this direction as well. Either way, we get this. If I want to use a delta pi. Now, intuitively, how much field penetrates delta S? More area delta A implies more field. And I said more field, more flux. And the field more perpendicular to delta F implies more flux. That makes sense? You think of the electric field as something that's maybe kind of flowing through. So the bigger the area, the more field flows, okay? And the more the field is perpendicular to the region, the more field will flow through. If I have a fluid flow in this direction, then to get the most field or fluid through, say the circle here, okay? I wouldn't want to hold this thing this way because the field or the circle is pretty much parallel to the flow. So not much flow gets through here. If I turn it this way, then a lot of flow will get through, right? And the less parallel it is, I'm using parallel and perpendicular and so forth ambiguously here. Let's be careful about it. We got a normal vector. So normal vector is like this, and the fluid is flowing like this. Nothing really goes through. It only, the boundary is infinitely thin. Pretty much nothing gets through. If it's like this, I'm intercepting the maximum amount. If the normal is at an angle of 45 degrees to the fluid, then I'm going to intercept an amount that's proportional to the cosine of 45 degrees, okay? A component of the fluid flow in the direction of the normal vector. Hopefully that makes some kind of sense. And it should make increasing sense when you see other explanations and start dealing with it. Okay, so the bottom line from this okay, I've introduced the delta S as a surface increment. The area delta A wrote that just now as a vector delta A without defining it. Delta phi E is E dot N delta A. Okay, the component of E normal to the delta S increment. So like if you have side view, your normal vector like this, and E vectors like this, the component of E in the direction of the normal vector is just a projection of E on the normal vector. I don't have a good place to label the normal vector. Picture three before I do it. I define it like this. This vector is the magnitude of, this vector is EM, the part of E normal to the surface. And the magnitude of EN is just E dot N, where N is a unit normal. Okay? That makes sense. What you're seeing is the electric field is this big, but this is a little bit smaller because not all the electric field is moving in the normal direction. Not all the electric field is penetrating. There are other ways to draw it, but we'll stick with it that way. In any case, here's your definition. Well, if you do E dot N times delta A, that's the same as E dot N delta A. So delta A is just a scalar. And think back to why that's so. So this could be written as E dot delta A vector, where the delta A vector is your N times your delta A area. So it comes down to a pretty simple picture. You got some area increment here. You got a normal vector, and you got some field. Field might be a flow field, it might be a magnetic field, it might be an electric field. The flux is the amount of that field that's flowing through this surface. And the more the surface is perpendicular to the direction of flow, if you want to go slow, the more of that flow will go through. Okay. Well, anyhow, don't really get to Gauss's law here. So now my question is, with the sun over all increments, now I'm kind of waving my hands on that, but all increments, in other words, we divide the whole sphere up into little tiny increments, okay? What's this sum? And let's say Quite more than I intended to. Okay, so these would be equal increments of surface area covering the entire surface without overlap. That incidentally is pretty hard to do in practice on a sphere, but I'm not going to worry about that. Theoretically, we can do it. So we're doing E dot N dA. Okay, question now is what's E dot N? Well, what's the direction of E? And we had to sort that a little bit, but something says directly away. Okay, that means radial in this case. It's directly away from Q. It's in the direction of the R vector. It's radial. So what's the direction of the normal vector? It's radial outward. Now, is E radial outward or radial inward? That depends on Q, whether it's positive or negative. If Q is positive, then it equals, maybe I should have just put E down there. Okay, we'll say this way. It's KQ over A squared. If Q is positive, and you know what I'm writing is I'm pulled up. So let me write it. I'm going to break it into two cases, but it is just plain old KQ over A squared. Because if Q is positive, then both N and E are radial outward, and the dot product is just equal to the product of the two because they're parallel. If Q is negative, then E is inward, and you're going to get a negative result. Well, that's what you're going to get if Q is a negative number. Okay, so it's positive or negative as Q is positive or negative. Okay, well, then E dot N is a constant. It can be pulled outside of your summation. It's a distributive law. You know, put it outside here. It still multiplies every one of your DAs by the distributive law. What's the sum of all your DAs? Sum of all your, actually, I'm using delta A. No, I'm using delta. Okay. I should be using delta. So minor point, but we want to be careful. Just in case. What's the sum of all your delta A's of your surface increments that cover the entire surface without overlap? Well, the sum of all the area increments, we divide surface of the sphere up into little non-overlapping increments. And it actually doesn't matter if they're equal increments or not. So I could take equal out of here. I had it equal because I wanted to be able to factor these out, but it's the E dot M that you're factoring out, so I just wasn't thinking clearly. So we remove the assumption of equal increments. But the assumption isn't a bad idea, because we're gonna take a limit as these things go to zero and get an integral, but this sum is equal to the total area of the sphere AQ over A squared times 4 pi A. Now, just one comment, when I took calculus, I mean, I learned the formulas for all kinds of things in high school. So I knew that the volume of the sphere is 4/3 pi r cubed or A cubed, and the surface area is 4 pi A squared. Okay. And I learned how to reason out a lot of other things. So one of the neatest things I learned in calculus, because I had trouble visualizing the solid geometry that you can use to get those results. The neat thing is when I went into calculus, I was able to set up and do the integrals very easily for the surface area and volume of a sphere. So if you can't do those integrals, this is a good time to review because you're really going to need to understand them within a few weeks as we get into volume and surface area in integrations in multivariable calculus. Okay. You really, really need to be able to do those kinds of integrals in order to do the kinds of integrals you're going to be encountering. It's just standard calculus 2 techniques. You know, a lot of sign substitutions and trigonometric substitutions and stuff like that because of the geometry of things. You want to be up on that. You don't want to go into this stumbling over simple integration. Oh, that's not simple. I mean, it is something you can stumble over at first, but you really have to master that. If you don't, then you're going to have to master in this course on top of everything else. So you're going to be better off if you master it before you see it there, so you're not losing the idea when we get to it. So take that as a bit of advice. Anyhow, okay. So and it's 4 pi A squared, not 4 pi A. Okay. I couldn't remember that. Well, being careless today. Okay, well, that's just four pi K cubed. Okay, well, I'm going to write down Gauss's law. Total flux of field due to a charge through a closed surface and closing it is 4 pi k cubed. Now that will be something we prove, as it's one of the most important relationships in the universe in monoidal calculus. Right now, you can accept that it's true. It's true no matter what the shape of the surface, and no matter how the charge is distributed within the surface. So for example, let's just say you got another sphere. And here's the center. And out here is a charge Q. Within the sphere. Well, we'll do another sphere. They're very easy to visualize. You got Q1 and Q2 here. That's 4 pi k times Q1 plus Q2. You've got a sphere with a blob of charge. Okay, so you got this blob of charge, whatever it looks like. It might be a uniform distribution, it might be a non-uniform distribution, might be irregular as heck, it doesn't matter. You spread that much charge in there, no matter how it distributes itself, the total flux through that sphere is going to be 4 pi k cubed. Now that doesn't help you if you want to find the electric field at a point on the surface. Why not? Because unless the charge is at the center, or unless the charge is distributed symmetrically about the center, you can't say that the field at the surface is normal. A little bit of a long statement. I'm saying not going to help if the charge isn't spherically symmetric in some sense around the center, since a field won't be normal at every point of the surface. Clearly, if the charge is here and the center is here, then if we look at a point here on the surface, the surface increment is normal, but the field due to this charge is here. E is not normal. Okay, there are a couple of points where it would be if you do a radial line from the center through the charge to the surface. At that point, the field is normal. That's the only point where the field is normal, except the one on the other side. The antipode, okay? Antipodal point. That halfway makes sense? Well, it should when you read it. Do the sort of problems. Now, a couple of cases where this does work. Okay. An infant line charge of constant density lambda as viewed looks like this. The surface that we're going to put around it is, well, we just put a big old cylinder around it. And if it's an infinite line charge, we can use the cylinder around any segment of this thing. If the cylinder has length L and radius A, then by the symmetry of the distribution, if we look at an M picture of this thing, by the symmetry of the distribution, the field always has to be radial In other words, if you have an infinite line chart and rotate it a little bit, it's not going to affect the field at any point. Meaning that the field has to be radial because it was off radial here, and then you rotated it, then it would be off radial down here. Okay, and it wouldn't be the same. You know, it's off radial everywhere. If you reverse the thing, then it's off radial in the opposite direction, and same thing happens. So I don't have a lot of time because we're out of time, but this is an example, okay? So you got this symmetry of a radial field E. The flux equals just E times the area of the cylinder, which equals E times the circumference times the length. Because if you cut this thing and unfold it, you get a rectangle whose one dimension is the circumference, 2 pi a, the other is the length. Roll up a piece of paper, convince yourself of that. But this flux equals lambda times L. Okay, cylinder has length L, so how much charge does it enclose? That tells you that E equals lambda L over 2 pi a L. The L's cancel. So it doesn't matter how long you made that cylinder. And there you have it. Now notice that for spherical, well, a point charge, the sphere tells you, well, the area is proportional to a squared or pi a squared, okay? Giving you a field that's kq over a squared. Here, it's inversely proportional to a. So the field of a point charge falls off as the square of your distance. The field of an infinite line charge just falls off proportional to your distance. And it's going to turn out in a very simple argument that you're probably going to read. I hope you read it. We'll talk about it next time. If you have an infinite plane charge, it doesn't fall off at all. So the field between two capacitors, which are infinite if they're really close together, and essentially infinite at any point that isn't too close to one of the edges, you get the field of a capacitor and you get the whole definition of capacitance. So it's a lot to be learned here, but the general picture is just this: surfaces enclosing charges with a lot of symmetry. And if you don't have a lot of symmetry, it's fairly useless in most cases, okay? This is a result of polynomial calculus that we'll see toward the end of the semester. Gauss's law. And this is Gauss's law for physics, okay? And these surfaces, the sphere, the cylinder here, are called Gaussian surfaces. Again, worthless in a case like this. We don't have a lot of symmetry, but if you have a lot of symmetry, it's really, really useful. And you have a lot of symmetry in a lot of electrical devices. You build them that way so you have the symmetry. Also build them that way because that's the easy way to build them.